Hello again to quantities in chemistry. So in the last video we all learnt a lot about the mole, and now we're going to start using the mole and the mole concept in a variety of situations. So we're going to, in this video, look at changing moles to number of particles and number of particles to moles. Now on your information sheet on page 5 you're actually given the formulas that you'll be using. You're also given Avogadro's number, which is for us is given the symbol Na, and in this video we're going to make use of this formula here predominantly, where n is the number of particles, equals little n, which is the amount of a substance. Now in chemistry the amount of a substance is in moles. Students sometimes get thrown by that, because if I asked you for the amount of something, you might give it to me in grams or kilograms or things like that, but in chemists the amount of something is in moles without the E, and there we use Avogadro's number. So the number, N, the number of particles, equals the amount of the substance multiplied by Avogadro's number. Now we also have this one where the number of moles of a substance, little n, is equal to little m, which is mass, divided by capital M, which is the molar mass. Remember we worked out the molar mass last video? Now notice that this little m, the units in chemistry, the standard units are grams, whereas in physics we used kilograms, just to confuse you. So all that's on your information sheet. You don't have to memorize it. So this time we're going to go counting particles, and we're going to be changing moles to the number of particles. Now let's imagine a gas bottle, and in that gas bottle we've got 1 mole of carbon dioxide. Now carbon dioxide is a covalent molecular substance, so we have 1 mole of carbon dioxide molecules. Now each molecule of carbon dioxide is a carbon with 2 oxygens. So if in one molecule we have two atoms of oxygen and 1 atom of carbon. Now that must mean that if we have 1 mole of carbon dioxide molecules in this container, it must mean that we must have 2 moles of oxygen atoms, because each molecule contains 2 oxygen atoms, and we must have 1 mole of carbon atoms. Now some students get confused by that, because here we're saying we have 1 mole of carbon dioxide molecules, and they think of a mole being 6.02 times by 10 to the 23, so it's a number, and then they want to go, well hang on, you're saying you've got 2 moles of oxygen atoms here and 1 mole of carbon atoms, that adds up to 3 moles, but we've only got 1 mole. But you see, with chemistry 2 plus 1 equals 1, depending on the situation, because we're counting different things. Here we're counting carbon dioxide molecules, and here we're counting atoms of different types. Okay, so let's just look at that. So if we have 1 mole of carbon dioxide molecules, we have 1 mole of carbon dioxide CO2 molecules. Therefore we must have Avogadro's number, 6.02 times by 10 to the 23 of carbon dioxide molecules. Also means that because there's 1 carbon in there, in the molecule, we only have 1 mole of carbon atoms. So we have Avogadro's number of carbon atoms. But there's 2 oxygens, so we have 2 moles of oxygen atoms. And therefore we have 1.204 times by 10 to the 24 oxygen atoms. And all this would weigh 28 grams. Counting moles to number of particles, or changing moles to number of particles. So on our information sheet we've got these formulas. The formula N equals M on M, little m on big M, where N is the number of moles, M is the mass of the sample in grams, and M is the molar mass, can be used to calculate the number of moles of an element or a compound. And the formula N, number of particles, divided by Avogadro's number, can be used to calculate the number of moles. So this one is actually just this one rearranged, and this one is this one. So, what does that mean? Well, we've got N, the number of particles, equals the number of moles multiplied by Avogadro's number. And you can rearrange this, or you can remember it one way or another. This is a way you sometimes see it. Here we have the number of particles, and here we have moles. So if we want to go from moles to number of particles, we times by Avogadro's number, and we get the number of particles. Now those particles could be molecules, atoms, or ions. If we want to go the other way, number of particles to moles, we divide by Avogadro's number. And that's just a rearrangement of that formula, remembering that it's on our information sheet. So let's do a couple of examples quickly. Calculating the number of particles, determining the number of atoms present in a sample. If we have a gas balloon, it contains 5.5 moles of helium atoms. How many helium atoms are present? Now helium is a noble gas, so it's going to occur as single atoms, and the number of particles will be the number of moles of helium times by Avogadro's number, using this formula here. And so we've got 5.5 moles times by Avogadro's number, and we get this answer. So you should be able to do these questions out of chapter 3. Let's do another example, determining the number of moles given the number of particles. Pure liquid ammonia is called anhydrous ammonia and is used as a fertilizer because of its high nitrogen content. If we have 4.6 times by 10 to the 28 molecules of ammonia, who would count that? But anyway, NH3 in the fertilizer plant store, how many moles does this represent? So we've got the number of particles and we want the number of moles. So using this formula but rearranging it, we want the number of moles, so N, so we would bring Avogadro's number across to here, divide the number of particles by Avogadro's number, so number of molecules divided by Avogadro's number, there it is there, 7.6 times by 10 to the 4 is our answer. And our answer is in moles, because we're after the number of moles. Should be able to do these questions now. Question 4 in your chapter. And in the next video, we're going to muck things around a bit and go from mass to moles and moles to mass. See ya.